Okay, hello everyone, and welcome to our live Q&A session. We are joined today from researchers from imec in Belgium. So imec is part of the EPICS Fab network, and they provide multi-project wafer foundry services. And their latest offering includes modulators and germanium detectors. So the two presenters today are Amit Khanna and Youssef Drisi, and they're research engineers, and they're working on silicon photonics, both on the technology side as well as the PDK development. So they'll be speaking with us about both how the technology works and what the PDKs look like. Hello and welcome. Thank you for joining us. If you can go ahead and share your screen and give us a presentation, then we'll have some questions at the end.
Perfect. Thanks a lot, Lucas. Can you hear me?
Yes, I can hear you, yeah.
All right, wonderful. I'll just switch the camera off at this point. Hello, everyone. And while I turn the sharing on, just give me a second. Do you see my presentation, Lucas?
Yes, I do. Perfect.
All right, we'll get started then. So, hello everyone again. Thanks a lot, Lucas, for the introduction. As he just explained, we are opening silicon photonics for users around the world to access for their R&D as well as low volume needs. We're going to break it up into two parts, me starting with an introduction to the technology, which is going to be like a premise so you understand better the contents of the PDK, which will be described by my colleague, Youssef Drisi, and especially focusing on the design environment in Mentor Graphics. The first part will be more general, telling you a bit more about the technology, what's the fab, what's the PDK overview, and how we provide access to users in a turnkey turnkey ecosystem for users to access in small volume. That's the schematic cross-section of our process, as will be available from the next tape out. So users can access two levels of metal, edge couplers, gratings with high efficiency based on a thicker silicon layer based on polysilicon, the standard edge levels on 220 SOI to enable rich waveguides, strip waveguides, and different kinds of rich waveguides with different profiles is possible. So you can get as many as 5 different cross-sections only based on edge depths, various cross-sections obviously based on your design freedom in plane. Apart from that, we also provide access to 3N and 3P type implant levels, which means users have a lot of flexibility in making their implant profiles and designing modulators with different kinds of performance. Together with that, we also actually announced, photodiodes were accessible before, but now also based on germanium, we provide users access to germanium electro-absorption modulators, which are extremely small in size and very high speed. And with a host of a lot of other components. So let's say that's how the cross-section of our platform looks like. It's based on a 2-micron box wafer, SOI wafer, with a 220 nanometer silicon layer on which we pattern our 3 levels of passives and the poly. To dig into a bit more detail, the poly is the second row there. It's called the FCW in our PDK. It refers to a 160 nanometer thick poly layer through which you can realize most devices, advanced grating couplers. Then there's 6 types of implants, as I just mentioned. Then there are the germanium modules to allow access to epitaxially grown germanium layers for photodiodes, as well as electroabsorption modulators. Then the standard back end of line, starting with silicide, tungsten, metal 1, via, and metal 2, pass, med pass, and then we open up the edge coupler module so that users can have wideband access through single channel to their devices. Also low loss compared to gratings, of course. I'll tell you a bit about how do we do process control. So all of this process is based on the CMOS line at imec, and that enables us to track each process step, each mask exposure, etc., with CMOS-like accuracy. We have standard structures on all our masks, which go through imec's CMOS line. It's based on the 193 nanometer deep UV process, which allows us to go all the way down to 100 nanometers in line width. We track 132 parameters varying from thicknesses to alignment accuracies between mask layers to CD control, etc. So there's a lot of different parameters. The fully complex version of our process already includes about 33 mask levels. So that's really complex. That's as complex as some of the CMOS technologies. And so a lot of monitoring, et cetera, is needed to make sure that at the end of that process, everything turns out right. And we do that. And it's all trend charted. So this is an example of a trend chart. This is an example of how well the top silicon thickness is controlled. As you would know, silicon photonics is a high index contrast optical platform, which means that you have very tight, let's say, specs needed to get your devices on target when it comes to patterning of silicon. A nanometer of variation in thickness can correspond to a nanometer or 2 nanometer of shift in ring resonator spectral behavior, as an example. So you want extremely tight control, right? And it comes with CMOS, but it's also needed. It's essential. And so this is an example of how well the top silicon surface is controlled prior to processing. It's within 2 to 3 nanometers, mean about 222 nanometers, and that's for the top surface of the SOI wafer. We do 49-point measurement per wafer, 1 centimeter edge exclusion. You can also see some of the raw data in the table below. But that's the kind of check we have on every wafer, every lot that goes through processing. This is data collected, I believe, over 1.5 years. So a lot of lots, a lot of wafers. And every lot that goes through such tracking, and that data is automatically gathered, just as is done for every CMOS process. And for all those 132 parameters that I described are tracked in the process. We also have end-of-line characterization. So what you get access to is reports from the runs, which tell you more about how does the resistivity of the contact or the implant layers behave. Also optoelectronic structures. So we qualify wafers based on these results before shipping to clients. The idea of explaining all this now before digging into the PDK is to tell you that the PDK itself is populated with data coming from such tracking. So the data that I'm showing here, or the processes that I'm explaining, the way we acquire data, all of that is then crystallized into the PDK, summarized in a form that can be easily assimilated and used for your simulations or for your better understanding of the process before doing design work and layout. So there's a lot of different structures. What you're seeing on the screen on the top part is an electrical test suite, which includes Van der Pauws, chains, kelvins, etc., for various different combinations of the back end of line stack. What you see at the bottom is a standard optical optoelectronic test suite, which includes various kinds of cross sections of waveguides for characterizing loss, as well as photodiodes, heaters, traveling wave Mach Zenders. Those are the 2 long patches on the right, vertically oriented, and a lot of other components. I think it's worth mentioning that these sites are also very standard. So they are repeated run after run and are repeated on every wafer. And to a lot of users, we even supply these components so they can track their performance to make sure their measurement setups are well calibrated. That's our internal imec. Actually, we've expanded this. This is one of the setups. This is an automated test setup to do electro-optic characterization up to 50 gigahertz. So we load a wafer, we leave it there overnight, and next morning we have the whole wafer for the standard test suites that I just described on the previous slide characterized, and then data analysis is also automated, so we can actually see that the wafer is good enough for supplying to clients or not. And then all of this data falls into the PDK. I'll tell you a bit about the device performance. We have over 50 components in our PDK in both the C and the O band, and giving you a lot of detail on, even now we've expanded it to include even statistical variations of performance of components for the key functional performance, to describe their key functional performance. The table here shows maybe small font, but the table here shows a lot of different components that we have in our PDK with listed MAT. That's the last column. That is telling you about the maturity of the components. So we release components with different levels of maturity. If you've signed our NDAs, you can go into this manual and actually look at how many data points do we have for each one of the specified parameters for a component. For some of them, it's more than 2,000 points. For some of them, it's just 50. So it's a young component, and users must bear that in mind while they're using them in their designs. Anyway, there's a lot of detail in the handbooks, and you're very welcome to look at the performance of all the devices in there. Just to highlight a few of them, the germanium electroabsorption is not mentioned here, but can go as high as 50 gigahertz. We are suggesting our users to try out advanced modulation schemes based on that. It's an extremely small component, 20 micron size in length. We also have a lot of components here, such as germanium photodiodes, ring modulators, traveling wave Mach Zenders, and a host of different fiber grading couplers and waveguides, both for the C and the O band. So the data in our PDK is always populated with both for both the bands. To go into a bit of more detail to show you how the spreads across the wafer look, this is an example of the grading coupler performance for the higher efficiency grading. Typical loss or insertion loss for these gratings around the peak wavelength is about 2.5 dB, and their bandwidth is even higher. It's usually now in our latest results in the PDK, it's closer to 30 nanometers. And we have a within wafer peak wavelength variation of about 10 nanometers. And a dominant part of that is coming from line width control across the wafer using the 193 nanometer DUV. So that is quite good when you compare it to, let's say, DUV done with 248, etc. So we see a clear improvement on that. That's an example of the kind of loss numbers we see on our passive waveguides. The leftmost is the cross-section of a strip waveguide, 450 wide in design. Always design. The numbers you see, 450, 500, and 650, are all as designed, not as yielded on the wafer. And the details of how they yield on the wafer are also always included in the PDK, telling you precisely that if you make a design of 100 nanometers or if you make a design of 500, how is it going to print on the chip? So providing you bias tables to correctly bias your devices to get them right according to your design intent. There's a big gap. You should know that in lithography, all non-CD geometries always have a bias. So that's an important side remark. But each one of these waveguides have fairly well-controlled loss numbers. So the 450 strip yields an average mean loss of about 1.34. And you can see the distribution across the wafer on the leftmost wafer map. So it's very uniform across the wafer. By the way, all these measurements are done with an oxide clad. So it's not air clad or side oxide. And the oxide thickness is about, in this case, I believe about 2 microns. And so on and so forth. So as you go into a rich waveguide configuration, as is FC650, then you obviously have lower loss in the waveguide because the mode is larger and less of the sidewall is visible. Moving over to active components, this is an example of performance of our traveling wave Mach Zender device. The device, in fact, has much better performance now. We have on-chip termination, which provides even higher speed performance. It is benchmarked to get with some of the performance from, let's say, other fabs as well in one of the papers that is linked below. The length of the device can vary from 0.5 millimeter to 1.5. The traveling wave version is 1.5 and has a VPi LPi of about 0.7. So, and we also provide different kinds of implant conditions so users can play with them to realize their own components. The speed for this device is shown to be 10 gigabits per second. The eye is fairly clean, also 25 gigabits per second, but we've shown this device can go as high as 40 gigabits per second with on-chip termination. And that's our latest component in the library. Not shown here. This is an example of a user who used our platform to design let's say, modulator devices, and they could show that the same implant conditions could be used to go for higher speeds, much higher than the results that we had shown in our PDK. The idea is that the PDK and the library components in the PDK act as a tool to show that the platform is capable to deliver components. It's not a fully explored parameter space to show you the golden device possible on the platform. So that's something the users are free to explore and optimize and get higher speed, higher functionality devices. That's an example of our ring modulator that has about 7.5 micron radius. The this is using a socket etch level, which is the deeper etch on the SOI. And although the results here include tungsten heaters and the undercut for enhanced thermal efficiency, the results that are for the component in the PDK go as high as about 22 gigahertz. So some of the eye diagrams at that speed are also shown here, going for 28 gigabits per second there, compatible with the 25G performance. Looking at the photodiode, this is an example of responsivity, dark current, and the bandwidth for the photodiode. This is a cross-section image on the top left for the germanium device. We have three kinds of components in our PDK, going up to responsivities as high as 0.97 amperes per watt. And the latest components that we're planning to release in our upcoming release are going as high as 1.1 amperes per watt. And a lot of statistical data about the distribution, etc., is included. One of the things that stands out is the excellent control on dark current, and dark current for all of our photodiodes is definitely below 30 nanoamps, and this is also a safe number. We see much better performance actually. So the numbers we supply are also usually the numbers we feel are safe to deliver to customers. So there's really not a lot of chest thumping going on there. That's again an example of how let's say the dark current is calibrated. So in the PDK we mentioned it's about 50 nanoamps, and so what you see at the bottom on the colored curve below is lot 1, lot 2. Each lot is about 23 wafers, and we marked the difference in performance on each wafer and the spread to show you how well the dark current is controlled. Just as an example for one of the devices. To give an example of what can be done with silicon photonics, you can bond it together with CMOS through flip chip. This was a demonstration done at imec through copper pillar approach, and the driver electronics was on the CMOS, and the upper part is the transmit circuit, and the lower part is the receive circuit with a 12 fiber array, bringing the signals back onto another silicon photonics chip. And here we demonstrated a 20G performance per channel, and we demonstrated this for 4 channels. And this was using the silicon micro ring resonator modulator. Now moving over to the PDK. So all of this, what I've shown so far, is available in open access, except the fact that the micro pillar that was used for this demonstration is not, and neither is the undercut and the tungsten heater that I mentioned for the performance of the ring resonator. The rest is available. And how do you access it? Now that's the key question. How can users access this capability? We enabled that. For sake of time, I will skip let's say the initial introduction of the need for a PDK. I think we understand the PDK enables you to access the technology fabulously and reduces, let's say, the barrier to a successful design in as short time as possible. Now, I'll just go through the whole stages of developing a design in silicon photonics, especially if you're going through the imec fab. And it usually starts off with users doing simulations in their chosen environments, commercial tools or their own scripts, enabling them to do FDTD, FEM, FMM, BPM, etc., cross-section or mode propagation simulations. The interesting thing is that we provide enough statistical distribution in our PDK that you can actually predict the range of behavior of your device during simulations. And that's a very powerful capability, to have statistical data to upfront understand how is your device going to behave, worst case, best case, after coming out of the imec fab. But that is not something that is directly enabled by us. It's enabled by data supplied by us in tools of your choice. Once you have your simulations done, you've got your devices nailed down, let's say, what you could do is build your own device models. Or if you want to build your circuit only with imec's library components, you can use device models that we have built with our tool collaborators. Using device models, you can then predict the behavior of your complete circuit with statistical variations. There's a lot of abstraction involved in this part of the flow today, but this is getting increasingly more mature, moving towards corner simulations eventually, but we're not there yet. So this is partially enabled through a really abstract level of circuit simulations, allowing users to get a general idea of if every device is working around its mean in real measured data in the fab, then how is your circuit going to behave? That is still very useful information. Once you've done your circuit simulations through device models, you move over to STL, which is schematic-driven layout. And actually, every stage following this can be enabled in Mentor Graphics. And I think that's one of the key elements for this session today. So starting from schematic-driven layout, moving over to layout, a GDS generation, which is compliant to imec fab requirements, is all possible in Mentor. That is the first part, right? That's generating your layout. The second part is verifying whether your layout is right or not. Although a lot of design rule aware intent is already embedded in Mentor's design environment, we still have formal checks and gates to make sure your designs are compliant, that we will do anyway, irrespective of the tools you choose. And there are two ways we do this. We do this through DRC and LVS. And DRC checks for manufacturability. It stands for design rule check. It checks whether each layer follows the conditions necessary for fabrication. It doesn't check for optical functionality. We have enhanced it to include certain level of optical functionality check, but that's really rudimentary. The primary purpose remains manufacturability. Also includes mask shop guidelines, GDS2 constraints, doing basic sanity checks on the script, etc. And then is the LVS. But these are parts that my colleague is going to cover in detail, so I'll skip them here and just give you a general big overview that the verification is using two gates. Another thing that we're working on is litho-friendly design. This may be of great interest to a lot of people who are really focusing on passive device design or doing subwavelength geometries or doing any kind of custom device design, because as I mentioned before, whenever you print your devices in through lithography, especially when it's through optical lithography, every geometry that is not the targeted geometry of the process will have a bias. So what you design, let's say you design A, there is no way around it. You're definitely going to get A plus a delta. It could be anything, depending upon the process. It could be, it's usually deterministic if the process is stable. So that's the good news. But how do you compensate for that delta already in your design is a big challenge, because a lot of designs going through silicon photonics. In our position, we see this because we see so many designs coming from all over the world. We see almost 50 to 70% of the designs are custom, which means most of the users are taking a risk in their first design cycles getting their custom devices on target. The chances are minimal, because what do they know about the process? Very little. It's the PDK which enables users through the bias charts that we provide. But again, using bias charts to manually correct your designs once you've done all your simulations is non-trivial either. I mean, you can only probably correct it for some parts of your key components, but certainly not for the whole circuit. So what's the way around this? And we're working together with Mentor to enable something called litho-friendly designing and photonics. And I think this is going to be a very key component moving forward. And the idea is that you design your custom component, you run it through an LFD simulator in Mentor, and that gives you a prediction of how this device is going to turn out after going through imec specific process. So we apply conditions which are specific to imec litho, etch, etc. And a lot more detail goes into that modeling, and that reduces at least, we think, 1 or 2 design cycles or participation cycles going through a fab. So therefore, making your design cycle extremely efficient and productive. So that's LFD. But together with that, we are also working on enabling OPC, which is optical proximity correction, a standard process in CMOS for correcting designs with certain changes so that designer's intent is matched. But we're planning to implement it in a very different way than is done in CMOS, not on the whole mask, but on selective areas. But this is only going to come out in the future. It's not there yet. It's something we're developing, and we'd like to let you know what we're doing. So that's why it's here. And all of this is empowered with data collected from the fab, right? So that is device testing, end of line, in process, and all of that is augmenting the whole design flow with validation, with data coming from the fab, so that your risk in accessing the run is minimized. And all of this is included in the PDK. To give you a snapshot, our PDK has various handbooks describing the technology, the layout guidelines, the library details. And today, what is available is going through the whole layout cycle and gating through DRC. But very soon, in September, you will have LVS, and in the first quarter of 2016, we plan to release our LFD and OPC capabilities. I'd just like to conclude by saying on the PDK that we work with various tools, but the scope of capabilities within Mentor is quite phenomenal, and we're also working extensively on building complex device models to enable eventually corner simulations. So the PDK enables you to go all the way from your design in your lab. You don't have to go into the fab. You follow the rules, follow the guidelines, right, to all the way to a chip. And in the case of imec, you can also go a step further and a step backwards as well. And I'll explain how backwards and how forwards. So we're trying to enable what's called the turnkey low volume capability in silicon photonics, building on our expertise together with CMC Microsystems in Canada, who are our design aggregator, part of our design aggregator network, supporting us in PDK development and also maturing the technology. So we're working with various CAD tool vendors to further enhance, let's say, the capability for users, going all the way from circuit simulations to advanced verification to advanced even fabrication mimicking, as you just saw previously with LFD. We're also working with design houses to provide users access to IP that is not otherwise covered in fab libraries. And this opens a whole new door of, let's say, ecosystem maturity. So that's the step prior to accessing the technology from the fab or through your design aggregator network, which could be CMC in Canada, which could be Moses in the US, or CTC38 in China. And of course, the two fabs that we're providing access to is imec and Leti. And you can also get your devices packaged. And that's the step afterwards. So you can follow our design guidelines, going to our website, and then make sure that your fiber couplers or your bond pads are laid out right so that they can be packaged once the devices are ready. So that in a nutshell is what is it in open access that you can get access to. And it's really growing fast. And it's a very exciting time to be involved in this field. And if you're doing R&D in this, it's really the perfect time to try out all these full ecosystem capabilities, starting from the design flow, going all the way down to packaging. What we did not cover in this part, and is also the part of the portfolio of imec's capabilities, is the 300 millimeter platform. Now, I wouldn't mention much. I just want to let you know it exists. The capabilities for 300 millimeter going from passive devices to actives. It's a completely different level of maturity. Of course, it's much more expensive, but the line widths you can achieve are going down to 50 nanometers, 80 nanometers, wafer scale, 300 millimeter, lot more dies, financially very attractive, but at the same time pricey if you want to do low volume access, which is why we don't open it up for MPW, but this capability exists and is also published. So if you want to know more about it, feel free to send me an email. I can forward you some of the results on 300 millimeter. We did not cover in detail, in fact, we didn't cover at all, imec's optical I/O R&D program. A lot of what you're seeing here, in especially the fab capability from imec, is coming out of the developments ongoing on the optical I/O R&D program, which is geared towards chip-to-chip interconnects, as well as further short-reach interconnects on chip, and it is geared towards really low-power optical interconnects on chip. So what we're developing here is all a trickle-down effect of that R&D activity, and also imec's silicon nitride program for life science applications. We didn't touch on that either, and that is also running on the CMOS line. So that's it, and now I'll pass it over to Yusuf to tell you in much more detail about the PDK capabilities for silicon photonics in Mentor's software. Lucas, do you want to take questions now? Do you want to take questions in the end?
I was thinking the end, but I think there's a few questions in particular. It seems like there's a lot of people wondering about how to access the PDK and whether it's open source or whether it's whether you have to have an agreement, signing the agreement before you get access to it, and do you have to pay to get access to the PDK, or at what point in time do you have to pay? So maybe you can describe that.
Yeah, I should have probably covered it in my slides. Yes, no, you don't have to pay at all. All you need to do is sign our NDA, and I can. The website is www.europracticeic.com. I'll type it as I speak. Let me see if I can edit it.
I can share the link afterwards.
Okay,
Through.
so that's the website. Just go to our website. You just need to download the NDA, sign it, and send it to us. We create an account for you so you can access the PDK. That's free. There's no charge associated to that. But of course, accessing the technology itself has a charge, and that is publicly known. That's also on the website. It's not hidden behind anything. It's all open, and the program has been running since 2006. So yeah, there's nothing hidden there, and a lot of people have accessed it. In fact, to give you some numbers, we have served designs. I cannot give an exact number because we work with a lot of design aggregators, but we've served over 500 designs since 2006. So yeah, a lot of users from research to companies have accessed the program and have benefited and have also moved over to production for some of them.
Very good. Do you know if there's any restrictions on certain countries based on, for example, like Iran or other countries like that?
We do have a restriction to open access to the E category countries. I believe there are 4 of them. I don't know the names by heart. Okay. But the E category, we do have a restriction to open the technology to. Yes.
Okay. I guess people will find out about that when they request the NDA.
Sure. Just send us an email, and I'm sure we'll find a way to address your concerns.
Mm-hmm. Great. Okay. Yeah, I think so. There's other questions. Let's see. Maybe we'll take them at the end. There's a lot of other technical questions on modulators and detectors and things like that. So we could take those at the end.
Okay. I'll transfer it to Yusuf.
Unless it makes sense. Unless it makes sense to do it now. Is there? Because you guys have one microphone.
I could. Yeah. I think just from that point of view, as you just said, maybe it makes it a bit convenient if I take them now and then we address it.
Okay, so maybe let's start with technology questions, and then we can do the PDK questions first. Okay, so I'll just go through the list of some of the questions I've seen. So one is on germanium detector performance. You showed excellent performance, and you also show incrementally that it gets better and better. So what do you do to improve the performance of the detectors?
Well, a lot of this has got to do with, well, that's not the only thing. There are various different aspects. There's the process, of course. The process in germanium is very sensitive. It's an epitaxial growth process. And what we have done so far is not open it for free design. We're providing users building blocks, which are black boxes. So you cannot freely design onto the germanium layer, but you can use our black boxes with known performance to put them on your circuits to have the photodetector capability. Now, we're doing this only because we realize the process is highly sensitive and we want to have good control and quality for the users first. Now, once this is even better qualified and matured, the design space is well explored, we'll open it for open access. I think that's one of the ways we are trying to limit risk on this process, because as you know, it's a germanium process with a high lattice mismatch, and you don't want to create problems in open access. Because in open access, users can submit all kinds of designs, all kinds of ideas, which is what we want them to as well. But just because it's early, we don't want to limit their immediate needs of getting a right working photodiode, because another user tried a really fancy design, and that caused a process window to be hurt. So that's one thing. We've not opened it for access. That's limiting the, let's say, the possibilities of things going wrong on a sensitive process layer. That's one. The other thing is that our team here has put a lot of effort into improving the way we characterize devices, especially active components. I can't go into detail, but that has contributed significantly to especially accurate absolute determination of individual library components, which, as you know, Lucas, can be a challenge.
Absolutely, yeah.
So, well, I can't go into the details of the measurement procedure, but actually, we've also added a lot of detail about how we characterize devices. How does the data that we report in our PDK, how do we arrive at that? So not just the component, but the test suite, the measurement procedure, the height of the fibers, for example, the probes we use, etc., the temperature conditions, etc. Everything is mentioned in the PDK. So users who'd like to know more about how the numbers we provide, we arrive at, they can get a lot of detail about that in our library handbook in the PDK.
Hmm. Yeah, I actually went through it recently. I was very impressed. I really like how you describe how you do the measurements and how you extract the data. So, for example, the discussion I found really interesting was Mach-Zehnder interferometers,
Hmm.
because that's one of the main topics in this course. So I really liked how you populated your PDK with information on that. So
Yeah, and this has just started. Only on the last version of our PDK release did we actually make those changes. So this is only going to get better.
great. Okay, so next question somebody asked on the discussion forum was for modulators.
Mhm.
What limits the performance in terms of fabrication? Uh, so what are the limitations in terms of performance? Can we get better performance in the future? What are the fundamental limits there?
I do not think we've explored the parameter space to mention how high, how fast we can go. In fact, previously we were even limited with our measurement setup in getting to know how high these modulators could perform. Um, so honestly, I do not have a very clear answer. But users of our platform have shown that the devices can behave much better than the components, even on the PDK. And this
Hmm.
is just by doing parameter sweeps, looking at the whole design parameter, let's say, options available to them. And we at imec are not, that's not our key mission to identify the golden device. So um, I don't think we have explored the entire parameters space to even mention what is the best possible performance. There must be theoretical limits for sure, but I don't think I have a number from the top of my head.
Hmm. Yeah, it's also been really interesting watching the community. People are starting to do higher order modulation and polarization, multiplexing, and things like that, getting very
Hmm.
high single wavelength aggregate rates. So it's quite interesting.
Hmm.
Okay, so the next question is quite a complicated one. This was posted by Bob last night. So he was wondering about active electronic components. So he has a background in CMOS electronics, and so he was wondering, one question is, I think the main question is why are transistors not included in silicon photonic processes,
Hmm.
and that there should be some advantages to having some localized transistors, for example, to drive large structures such as phase shifters of an amplifier. And then the primary motivation here would be to relax the requirements on the number of pins and the amount of power that has to go through the pins. And the idea here is that we're not trying to get the best 10 nanometer transistors in the process, but some level of transistors to help out and sort of partition some electronics in the most leading edge nodes and
Yep.
some basic
Hmm.
ones in the silicon photonics side.
Yeah, that's a very good question. In fact, at imec, I showed in the beginning the slide on the layer stack. Let me go back to that. And here we also mentioned there are two levels of implants possible on the poly. So that does open the door for someone who would like to explore those kind of devices. But we have not opened it in MPW. To customers who are working directly with imec, a lot of companies who are trying things out, this is a possibility. And the reason we don't do it is because what Bob mentions, there's interest in it, but not a lot of MPW users have expressed interest. And you know how MPW and open access works. There, it's important to make sure as much sharing of mask area and processes as possible. So gearing it up for 1 or 2 users out of 20 makes less sense. And that's the only reason. It adds to turnaround time and it adds to the cost. So that's the reason. But this process, there's no reason why it cannot be open, especially why? Because we're working on a CMOS line where implants on silicon is the way to do all devices. So indeed, I couldn't agree with Bob more, but we do have this capability without providing golden devices for users who'd like to make limited number of electronic components and test them out together with their
Mm-hmm.
photonics.
Mm-hmm. So I guess in summary, essentially, it's an economics issue of when it makes sense to integrate the transistors versus keeping them separate.
Yes. Also, we haven't, let's say, invested time into creating golden devices and libraries for the electronic side of it. So that's something that's completely open to users today,
Mm-hmm.
but also
Okay.
on a bilateral way, direct discussions with imec.
Great. Okay. Next question I see here is which tools do people use for modeling modulators? And I guess you showed a variety of simulation tools that you provide, and so if you can comment on how to design a modulator.
I'm not sure I know better than you, Lucas, but I'll try to answer. I think
It's okay because I haven't talked about this in this course at all, so it's a fresh topic.
Okay. We from what we understand, most users are trying Silvaco. That's one of the tools that is available where you can do implant distributions, but it doesn't immediately solve all the concerns when someone wants to do an electro-optic simulation for a modulator, because there you can do implant profile generation. You can do certain, I think it doesn't allow a complete simulation, but it does allow optical mode field to overlap with the implant and therefore apply voltages to see how the mode will eventually behave under the influence of the electrical field in the plasma dispersion kind of devices. But users also use Centaurus, which is, I think, a Synopsys extension for looking at other devices. Those are the two tools I'm aware of. Apart from this, I believe a lot of users may have their own scripts. A lot of research groups are doing it themselves. But I'd like to hear from you, Lucas. What do you think about this?
Mm-hmm. Yeah, well, I think there's several parts. So the first part you mentioned was simulating the process simulations. So we've done some of that work using, like you mentioned, Centaurus process. I think one of the challenges there is it's the information that's provided in the PDK is typically insufficient to do an accurate simulation. So in some of the earlier work we did with this it was you can get maybe 30% accuracy or something like that, but it's unless we were provided a doping profile to validate our models. Usually it's the foundries and the CMOS fabs that usually spend a lot more time on the process simulations rather than the end users. So I think for where I think users really should start modeling detectors is if you have a known implant profile, then you can do the electro-optic device simulation. So we've been working with Lumerical for that. So the tool that we use is Lumerical device, which is in a sense similar to a Centaurus device and some of the other ones that you mentioned as well. But yeah, so I think the main feeling is that process simulation is too close to the foundry and too difficult for most people to try, and it'd be if I was to put in a request for you, it'd be if you could provide us a depth cross section of doping as a function of position in the vertical direction for each of the dopant levels, and and then also I guess in the other dimension as well, the straggle in the lateral direction. So that would greatly help. But that said, I think it's also possible to use relatively simple models for the doping. You can use either a uniform doping density model or some sort of Gaussian type distribution, and if that's calibrated to like if your dopants don't change, and I understand doping is a very well controlled thing in the CMOS field, and so if you can come up with a model that's stable and accurate, sort of with either uniform or Gaussian, you can reuse the same model over and over, and then change your for example, do the interlaced junctions or changing the junction geometries, and then. So that would be a kind of a good point, is to have a model that's calibrated, and then people can make their own PN junction simulations. And then the final comment was that probably at some point in time people will want to avoid doing that altogether, and people will just start with the phase as a function of voltage characteristics for a specific PN junction, and then put that into a compact model into a circuit simulator. And then also loss versus voltage, and then the RC time constants and things like that. So that would be a compact modeling approach, because the design of traveling wave modulators, most of the challenge I think is actually in the microwave design. So really having a compact model for the junction would be kind of the way to go there. So.
Very good. I actually took note of some of the things you said, especially with regards to what the fab can provide to enable users to do this. I completely agree. Numerical device is also a very interesting tool to do this. In fact, we're also, you may see a change in the list of tools we support very soon. And yeah, the last part, especially that you mentioned, Lucas, on compact models, I think that is the way we're gearing to go now on, especially developing it for all active components, trying to minimize the effort on the user to actually go through the whole cycle themselves.
Yeah, no, I think that's really critical. Some of the publications I enjoy reading the most are the ones that where they don't just say, here we made a modulator, here's the eye diagram, but they actually characterized the S11 RF performance of the modulator, and then
Hmm.
based on that, they built a compact model that they show what are the the equivalent RC parameters for that junction or as a function of length and so on. Because then the subsequent designer can say, oh, good, okay, I'm going to start with that, but then I'm going to
Yeah,
put my
yeah.
traveling wave structure on that. And there are some nice equations. Lumerical interconnect has a really nice model for a traveling wave modulator where you basically
Hmm.
put in these lumped element models that
Yeah,
are either from the foundry or from TCAD simulations, right?
yeah. Hmm.
Okay, so that's anyways, that's a very interesting discussion topic. So the next question was, the question was really about the simulation side, but probably it's a more fundamental question about amplifiers. Is there a way to include an SOA in your process or any other silicon process for that matter?
Not that we offer it yet. Uh, Not to our knowledge at the moment.
Hmm.
Are you aware of something, Lucas?
No, no, I'm not. No, no. I think adding 3.5 materials on silicon or other gain materials is something that I would
That's
love to
true. Huh?
see that.
That's a different road. I agree. I mean, playing with 3.5 together with silicon, that opens the door to a lot many possibilities, lasers, SOAs, some of the key components missing. But yeah, monolithic on silicon, a bit
Yeah,
challenging
no,
at
I'm
the
not.
moment.
Yeah, for me, monolithic is not the one I'm thinking of. Is more the 3.5 approach,
Sure,
so that
sure.
you already have, like you said, 30 masks or something like that. It'd be
Hmm.
really nice if there was a mask where I could just draw a little box of indium phosphide. That would be, that'd
Yes,
be my
yes.
dream from a.
Indeed, we wish we could. Actually, I should mention in the same breath that Leti has demonstrated processing of indium phosphide on silicon. I mean, and they've shown lasers on silicon in
Yes.
CMOS fabs. So there is. I mean, it's not that it's a shut door. I mean, there are possibilities. We at IMEC are
Mhm.
not taking that route, though.
Yeah, yeah. No, I know there's lots of research results. I think, and
Yeah.
there's a lot of groups in the world who have, and several companies who have shown this. It's
Hmm.
I think the question is that, when is this going to be available in the MPW? And
And
again, I
reliably.
suspect it's a
The
question
question
of
is
and reliable. Yeah.
reliably. Yeah, and wafer scale, and those are key questions. The results with molecular bonding, BCP bonding, and the whole body of work regarding integration of 3.5 materials with silicon. But how do you do it in a fab with minimal, following the same procedures and practices of a CMOS fab? I think that's the key challenge.
Yeah, and we've seen Intel delay their product shipment, which they didn't describe why, but one might suspect what is the least reliable part, and I would suspect it would be something to do with the 3.5
Hmm.
silicon integration, right?
Hmm. I would think so.
Hmm. Okay, so these are the questions I see so far now on. Actually, let me just check my list to see if there's anything else. Yeah, actually, I have a question for you on the lithography
Hmm.
simulation. So you're clearly calibrating this for your process, from what I can see, including both the sort of variations in the width and also the shrinking of the features.
Yeah.
Um, are you testing this on Bragg gratings as well?
At the moment, this is based on a flow which is actually prescribed by Mentor. And we were
Hmm.
inspired by a couple of publications that came out from your group, Lucas, where you had shown a zero level, I believe, model of LFD using it to predict how devices will turn out. And we really got inspired seeing that. And we thought, you know what, we want to do this with our process, really
Hmm.
get into the details. And no, at the moment, it's not using a Bragg, but Bragg-like structures. So there's periodic structures, there's different kinds of pitches of lines and spaces, and it will help designers who are looking for gradings and those kind of components to get their designs right first time. So indeed,
Hmm.
with not specifically that as the goal, but Mentor has a prescribed test suite which is used to generate algorithms and do the processing or the background number crunching to get the right results out of the fabrication simulation. And we're using their proprietary design. So it's
Hmm.
very closely knit with Mentor, not specifically geared for photonic components, but it will benefit them, absolutely.
Yeah, no, so I guess that's kind of the question I have in the back of my mind is how well is this approach going to work? Because that approach is based on rectangles, and and so on,
Yes. Yes.
and based
Linear
on taking
geometries. Yeah.
SEM images of the structures.
Yeah.
Whereas in contrast, the alternative way is to measure the performance of optical structures. And what's nice about the Bragg gratings is that it's the bandwidth of the grating is very sensitive to how the teeth turned out, and so it could be used as I guess maybe as a validation step. So once you
We're
have a
working on
model,
that. We're
I'll
also
be
working
curious
on that.
to.
Yes,
Yeah.
absolutely. We're looking at optical device performance to track back the replication of geometry during fabrication. So we're using that method as well. And that's a very interesting way to look back at how fabrication proceeded. And yeah, we're looking at that as well. Yes.
Okay. Maybe since I have lots of questions, so I'll ask one more question here. This is on, you show lots of statistical data on wafer to wafer and within the wafer variations. So these are all individual point devices where you're assuming essentially it's an independent random variable, and you can draw a histogram for it. But what I'm wondering about is correlations. So for example, if you have a Mach-Zehnder interferometer, and it's actually been really interesting in this course that we're doing now, we had 140 designs, in total I think 1,500 Mach-Zehnder interferometers, something like that. And if you look at all the different interferometer designs, even with the design freedom, there's one of the things that we're finding is that you can get a differential fabrication error, especially if the process is not as stable as yours is. And so one of the things I'm wondering is do you have any ideas on how to whether you can measure that differential error, and whether that might eventually end up in the PDK somehow? And then I guess how would you include that into a design flow, like Monte Carlo or something like that?
That's been one of our biggest challenges, right? And it could appear from any stage. It could appear from random variations in the way mask is printed before processing, the process itself, and then the measurement, the repeated measurements that are done to collect the data. For example, you mentioned 140 designs. How reliable is the measurement done across those 140 different designs or users, etc.? So there's so many places the variation, the random part of it can come from. And we've spent a lot of effort trying to minimize and at least localize the spots of random variations, such as by first controlling thickness of the SOI. There's less control, it's random how it appears, etc. And following that, we have ways of looking at the masks that come back. How do we control the quality of the masks? How are the same designs across the same mask varying? And that essentially becomes our mask acceptance criteria. So that's another stage where we're trying to minimize these random variations. And then, of course, the measurement setup. I think measurement setup is one of the key parts here. How far is the fiber from the grating? What kind of cladding is one using? Then how well is the setup calibrated prior to measurement and across repeated measurements? The planars, let's say, the chuck on which the wafer may be placed or the chip is placed, how planar is that? I mean, these can seem like very trivial things, but can have a lot of impact on these random fluctuations one sees on collected data. So we've worked a lot on that, especially on the measurement and the process side, and the data we provide in the PDK. We really think moving forward, and the data that we provided now is getting really stable.
Yeah, no, I think so. Yeah, no, in terms of absolute control, I think you guys are definitely leading the way in terms of measuring this and all that. So I applaud your efforts and thank you very much. So that's great.
Okay.
Okay, cool. So thank you very much, Amit. So should we turn it over to Youssef?
Absolutely, Lucas. We shall move it over to Youssef now, and just give us a second while we switch presentations and the headphones.
Great, thanks, Amit. Hi, Youssef.
Hello, everybody. So I'm going to present.
We can hear you.
Yeah, okay, good. I'm going to present what I call the imec CMC PDK within the Mentor graphics environment, which is mostly Pixis and Calibre environment tools. And so we have for this PDK we have I would say unique collaboration between imec, CMC, and Mentor Graphics. Mentor Graphics being the software provider, CMC being the very active design aggregator, but also active into essentially developing this PDK for Pixies, Mentor Graphics Pixies, and imec being technology supplier and also been active since a few months now into also working in the development of new features in this PDK. So the CMC PDK is for the ICIP25G imec silicon photonics that Amit has just shown as just presented as a technology, which is like the technology that is available in open access, and it's based on Mentor Graphics Pixies and Calibre tools. And the main features is the fact that we have now the full component library available within the Pixies environment, available not only for the layout but also for the schematic entry, and which allow precisely new features like the LVS and the schematic entry. SDL, which is schematic driven layout, is now also available for the ICIP25G. And there are also some photonic specific layout options that goes together. Again, LVS layout versus schematics based on Calibre tool, design rule check, also based on Calibre tool, and something extra that we have developed and we would like to also to share in the future with the designers in open access. What will be somehow a sanity check that is based on Calibre DRV, which is a script that needs Calibre DRV for being optimized. So how does it show? So I take for granted the fact that some people have already some background on Pixies, and I will show how it shows within Pixies. This is a snapshot on what's available today in Pixies. So you would have, for instance, for the ICIP25G, the component library that shows the active and passive devices. There is a slide where I will expand this view and show all the devices that are, all kind of devices that are available in that, and many of them Amit has presented the performances of them. So you would have also documentation, which is the same as the one offered by Europractice. So you would have the library handbook, technology handbook, layout handbook, all this already included within the Pixies environment. And then you would have the caliber verification files, the rule files, so-called, for the GRC and for the LVS. What I mentioned about the sanity check is not part actually of the Pixies environment yet. We can imagine that in the future it's going to be included, but it's an addendum to that. And then all kind of technology settings, layer, so some layer settings, some cross-section settings, and some other features, photonic specific, I would say. So this is how it shows in the Pixies environment. This is expanded the imec library ICIP25G for that shows all the types of devices that we have, that today we provide, like bond pads for the active part. So you would have bond pads. There are some, I would say, subcomponents like the contacts. So contacts is not necessarily something that you use as a device, but it's something that is included in many of the active devices, like the modulator, like the photodiode, and so on. And we also provided if some people would like to make their custom device. So you would have detectors, modulators, and phase shifters, which basically two different type of phase shifters, resistors, and then you would have the passive devices, mostly crossing. One crossing, we have the fiber grating couplers. We have different types of fiber gratings, also different types of MMI, and some examples of the layout is really put there as an example for if you want to have a transition between two types of waveguide, and if you want to see how the waveguides are drawn. It's not really a device, and each device has a set of files, three type of files. So you have the spice file, a symbol view, and a layout view. And I will take the example of a fiber grating coupler. So for instance, here you will have the 1D FC curved grating coupler. So it has a name that is not necessarily easy to remember, and this would include three types of files. So in the Pixis environment, it seems that they have the same name. It's just the extension that is different. Okay, and then you would have the first one is the spice definition, and it's actually, I would say, an almost like an empty shell. So what is there is in spice syntax. This is the definition of the device, as in for including the name and the input and the outputs. In this case, for instance, so it's the name is FGCCTE FC1DC 625313. That's the name, and the inputs would be Z0 for the fiber input output, A0. This is the in-plane access to the connecting waveguide, I would say. So this is needed for the LVS, because I'll explain that later, and that would be in the future also. Today it doesn't include any, I would say, compact model, but we can imagine that in the future that can be used for allowing actual circuit simulation. That would be done, I would say. That's we would definitely work in this sense, at least. And the other two views, this is the device symbol, and that's again key. So we need to that for each devices for being able to allow circuit schematic entry and device layout associated for that. That's an example. I will give a series right now of symbols, because this is a key element in what we've done for allowing the empowering the possibility of schematic entry and LVS. It's actually the symbol, and here we have and those symbols, since silicon photonics is, I would say, this is quite new in it. So I know, Lucas, you have done quite some work in that in the past, but for imec this is still new, and we still have the necessity, let's say, of the community to adopt those symbols. That's an example of symbols for the fiber grating that we came up with at imec, which allow for fiber grating with a very simple symbol way of representing the fiber. It allows for a single fiber to output to a different number of waveguide, in-plane waveguide, and that is I would say, requirement due to the variety of type of fiber grating couplers that we do have. So inside you would have a symbol representing, for instance, on the top left, this is a curved fiber grating, okay, with one channel in plane. On the top right, for instance, you would have a straight fiber grating coupler with two inputs, input-output, and so on. So on the bottom left, that's 2D grating with two inputs, and bottom right, it's 2D gratings with four input-output in plane at access to the waveguide. Another series of symbols. This is somehow more straightforward, which is for the crossing for some MMIs. And on the bottom left, this is the bond pad, which again, this one is a symbol that is somehow a reuse of some symbols developed by Mentor Graphics, probably in coordination with the Lucas team. Another series of symbols that we somehow invented for the purpose of silicon photonics, which is the phase shifter on the top left, okay, photodiode on the top right, and the ring modulator. And again, the key here is that the community, this is somehow, it has to work as a convention, and the community, we hope at least, will be able to adopt this convention and use it for designing circuits. And sometimes it's not that straightforward, and that's the example that we have here for one of the devices of that provided by imec in the IC25G, which is the Mach Zehnder, the lumped Mach Zehnder, and obviously it has many more electrical entries for two input-output, optical input-output, and okay, so you could see that the two arms of the Mach Zehnder, there are represented some diodes, which is representing the actual PN junction of the modulator in each arm. And another not so easy symbol is the traveling wave Mach Zehnder, and that also is represent quite well what is actually present in the layout, which is like on the top you have from E0 to E4 the 4 bond pad access, and on the bottom from F0 to F4 another 4 bond pads that actually are shortened in the device and representing every time a traveling wave connection. Electrical connection, yes. So the schematic entry capability is key here, and it's provided by, it's a key capability from Pixis, and it's now possible to use it with the IC25G library, and it allows actual circuit schematics for two domains, which is the electrical and the optical domain. So that's an example of somehow a bit of an idiotic circuit that I made, but it was just to show that the electrical connections on top of the bond pads that goes to different modulators or phase shifters. Yes, and an example also of optical domain with the fiber gratings and MMI that goes again to ring modulator and phase shifter, and goes again to some modulator. And Pixis allows that. Pixis is also able to make sure that you do not mix and connect electrical with optical, which is a very key feature. Okay, and then from that you can have the possibility of the schematic driven layout, which is like you can actually auto-instantiate in your layout automatically. From the schematic, the tool will place, not randomly but not accurately either, all the devices that are part of your circuit. And the other advantage of the SDL is that it will show virtual connections that is represented in the schematic, and every time you would move around one of the devices, a yellow line will be represented showing the actual expected connection expected from the schematics. So this is very handy when you actually want to lay out your design. Some of the, and for instance, when you want to connect the fiber gratings with the NMMI, like shown on the top left view, one of the key feature again is a photonic waveguide that would allow you to transform this Manhattan routing into a photonics curved waveguide with the actual proper layout and proper cross-section that you expect today, there is available only one type of waveguide, but we are working so that we have not only the strip waveguide, but also all kind of cross-section like ridge waveguide, like rib waveguide. So we are working on that, and we are confident that we will be able to provide, thanks to Metagraphics and their support, let's say all different types of all the different types of waveguide that are commonly used today in silicon photonics. For verification, we have again LVS that verifies that the layout circuit integrity, that it represents actually what you have drawn in your schematics. We have DRC that ensures manufacturability, as well as it is capable of tackling non-Manhattan shape issues, which is very specific to photonics. So we had to come up with specific to silicon photonics solution, and I will touch upon the sanity check on GDS fine later. What is it that we are checking with this sanity check? So layout versus schematic will be very brief, which was I think just for the concept, for everyone to know, because so what we have done is that now that we have capability of actual drawing schematics, that's one of the example. Each device has its SPICE representation, as I've explained, which allow the tool to actually generate what we call a source netlist, which is like it shows exactly each device to which and its input output, what are the connection between all the devices. And the Calibre tool will do the same actually, but directly from a layout it will try to extract a netlist and see what are the connections to it. So you would have then two netlist, the source netlist and the extractive netlist. In Calibre, LVS will compare the two netlists, the layout netlist and the schematics netlist, the source netlist. That's how it works, and it mostly works from again from Calibre is somehow can run independently from Pixis, but in general it is called directly from Pixis when you have that option. And it runs pretty smoothly, I would say, when you all work within the Metagraphics environment. But again, this can be run outside Pixis for some people who are using other tools. Let's say that Calibre is probably a tool that is broadly used from in the EDA world as well as in photonics for verification, even when Pixis is not used for design. And the Calibre output is when the LVS is successful, shows a report like is here. So you would have a comparison between the layout, different ports, different nets, what type of instances that is recognized. So the LVS recognizes the devices and recognizes the net connectivity, whether it is optical and electrical. LVS gives the purpose of that is to give a higher confidence for the designer that the layout is functionally consistent. So it's very key for the designers because in a way in photonics we are a bit like in electronics, I would say 25 years ago, and you have to imagine that 25 years ago people used to plot their layout on a paper and start to with a marker to go follow net by net, I would say, and make sure that their design is consistent. So we are somehow with this LVS trying to narrow the gap of the time, I would say, between photonics and electronics, and we are trying to get closer to 2015, and that's quite important. We are really like finally with this feature coming to I would say modernity in terms of design, which is not straightforward because in photonics still due to the nature of it. And I would say that many tools do not start drawing with the schematics. So it's also, let's say, giving the opportunity of the designers to change their philosophy in the way of working and start with something more conceptual than hardware, I would say, and start with the functionality and the schematics and the simulation before they actually start with the layout. So it's really like trying to get to a change in philosophy, which would enable more complex circuits. Definitely, at least that's the intention, and that's the philosophy behind that. So for the design rule check, it's also based on caliber. It's necessary to check if the design qualifies for fabrication. This is really like a manufacturability check. Process of checking if design meets fabrication standards is called DRC, design rule check. This DRC clean file means like no DRC error, qualifies for fabrication, and ensure that it has a good deal, but it doesn't mean that the optical functionality is ensured. That's why the LVS is there again. Those are two different things. Okay. Single layer check. So what it does, so mostly we check dimensions. On a single layer, we would check for the minimum width, minimum spacing, maximum width, minimum area, maximum area. These are the things that are very common. Obviously, the minimum width and minimum spacing are the key checks here for the single layer, because this is what manufacturability manufacturer would supply as I would say the key requirement for mask making. Okay, but you may have other requirements more specific, like in the shape of it, like sharp angles. Some layers, like we have some layers that, for instance, have to be drawn in a very specific shape, like in a rectangle, for instance, or in a square, like for vias, for instance. And sometimes you also have some requirements on the number of vertices, like minimum number of vertices or maximum number, convexity, small notches. So you have all kind of requirements defined by the foundry that are tackled with this caliber DRC in different ways, I would say. And you would have a multi-layer check, which actually checks on if that's more like for functionality in general, more than a manufacturability, but this is still key for the manufacturer to make sure that what they receive as a design will be functional. So there are things like illegal overlaps, mandatory overlaps, enclosure, extensions. These are things that are very important. And just as an ID, DRC, the rule deck today of imec includes more than 300 checks, okay, of all kinds, between single layers to multi-layers. Okay, and there is something very specific to photonics, which is that the layouts are unorthodox if you compare to EDA, and we are working with, I would say, tools that are originally meant for EDA, so originally meant for Manhattan shapes. And photonics is all about spirals, is all about curves, holes. So let's say that the implementation takes into account that and is innovative enough for for just tackling this issue of non-Manhattan routing, for instance. Even let's say metal routing, which is like supposed to be not photonic specific. In general, that's the layout of a ring modulator. Even the metals are routed in a curved way, I would say. Okay, but we would have also kind of specific photonics layout issues, which is, for instance, all angles. So the minimum width is specific. The minimum spacing is also defined in a different way. All angles are to be allowed, which is not so common in EDA. We also have to tackle the singular points to make sure that it doesn't happen, and we have also holes that we have to measure sharp angles, snap to grid issues, notch and small notches, convexity, contact shapes. Those are a list of issues that the GRC helps to trace, to detect, and to easily correct. What is not covered today, and that's still something that in photonics is very important, which is like the periodicity of a structure, the pitch of structures, because there are a lot of, I would say, periodic structures. So we would eventually come up with some solutions for that to be able to measure properly this periodicity and those pitch, and also the density is not something that we are covering. We are detecting very well, but we are working hard on that, so that we can come with some solutions, and that there are some GRC rules for that. The sanity check. Sanity check. So again, this is based on Calibre DRV tool, which is a bit different, and that's a series of, I would say, of scripts that can run to detect illegal characters in the names of the cells, empty cells, rotated instances. So this is something that is quite critical in the flow. I would say it doesn't seem. Eventually, the layout doesn't show any error. I would say functionally, not even in terms of mask making, but in the process of there are some tools that complains when they see a rotated instance, so we have to detect that. The same as for the magnification factor. Not all the cells. The GDS format allows for some cells to have a different magnification than one, so we need to detect that. So at the hierarchy level, we no more than 32 levels. Black box integrity. So as Amit has explained, so we offer different black box, which is for the photodiode today, but in the future we may have more elements, and we have all kind of issues when replacing these black boxes with the actual devices, that the black box is either flattened, so it can't be replaced, either the origin of it has been changed, so the layout has been changed, and then when you replace, it doesn't fit anymore in the way the designer expected to see the device, or the naming has changed, for instance, and it's also not possible to replace automatically, I would say. So those are the things that we need to detect, and we also now have included also something to detect which version of components is used, and that the layers are consistent with the technology. So this is what we call today the sanity check. That's about it. So any question is welcome.
Great, thanks, Youssef. Okay, so some of you who are online right now, feel free to jump in with your microphones if you want to ask some questions.
Again, just as a comment, that we are showing what's going to be available, especially for the LVS, in September. It will be, and probably end of September. But that is, that is what we think to be like a great improvement in the for the imec CMC PDK.
Maybe I'll ask a question. So how do you imagine simulating the circuits? So you showed lots of work on the LVS and things, which is what you're doing is outstanding. But yeah, how would you simulate the circuits that you're drawing?
That's a good question, because I think that is going to be the next big topic in that. So we've worked on the schematic entry. Okay, that's nice. We are working like in close to release the LVS. That's also nice. But to really let's say consider the design flow as complete, we definitely need to include the simulation. And I think that still with Mentor Graphics and their tool Eldo, we would be able to simulate. We need to, and we're working on that. We need to provide compact models Okay, and the only big question is how does the tool Aldo specifically will handle two domains? That's that's still for me a question mark. Many people are working on
Okay, so,
that.
it sounds that's an interesting approach. You're thinking about doing something similar to what Luxtera did, where they used kind of the spice type. I guess they used Verilog A, and I think Aldo's is similar to that. But
Exactly.
essentially using kind of existing electronic
Yeah.
solvers to do both electronics and optics, right?
Yes, that's yeah. Again, I don't know if it's the best approach, but I'm working now with what is available as tools, and I think that's the immediate approach I can come up with. Like, okay, let's use what's already available because Eldo is also let's put it like that. It's also a great simulator. So
Mhm.
either we have
Mhm.
to
Yeah,
start
no,
from
no,
scratch,
I
either
think
we
it
have
makes
to.
sense. It's
It makes sense. Yeah,
Yeah, no,
absolutely.
it's a proven approach, I guess, and like I said, the fact that Luxtera is doing it. I think IBM is also has a PDK where they're using an electronic kind of spice type solver to do these things. The
Yes.
other approach that you can consider, and we had a demonstration of this in the course, was using uh, basically what you showed, which is the schematic capture on the Mentor Graphics side, but then Mentor Graphics exports the spice net list and interconnect reads that and does the circuit simulations and then returns the data, and then Mentor Graphics can display the simulation results. So in this course, just at the very end, we had a demonstration of doing this
Yes.
in Mentor Graphics provided a virtual lab where people could simulate the Mach interferometer, it's a dedicated optical tool that's doing the circuit simulation as opposed to
Which I also
an
think is
electronics
actually
solver.
a good way of doing it. That don't get me wrong. I think it's also a very good way, and I think that if we want to enable simulation, we also have to, let's say, to promote this kind of way of working, like external people, like say specialists in photonic simulation, to be able uh, to interoperate with Mentor Graphics Pixis. That would be awesome, actually, if we can do that, especially because of. But we still have to work on precisely on developing those compact models in Spice, for instance. Those things. So there is a lot of work still to do in that way, and I think that we still need to also to work on cooperation with specialist, I would say, in photonics simulation. That's also a very good way of doing. But I think that's still for electro-optical simulations, for circuit electro-optical simulations. There are still many challenges to tackle in that, and that's where I'm like probably tools specialists of in simulations like Aldo has a big part to do with that. A
Mhm.
big
Yeah, no, I agree with you. I think
with
the other comment I resonate with is earlier in your presentation you said that it's a kind of a big paradigm shift for people instead of starting with kind of a physical bottom-up approach, is that people are going to start having to use an abstract kind of schematic approach. And that's quite different for the community. The electronics people, of course, are familiar with this, and so some of the students in this course who have an electronics background look at this and think we're crazy starting with polygons and simulating waveguides and things like that. But that's kind of how I guess the history of photonics has been more sort of on the physical side as opposed to schematic and
yes.
abstract, right?
Yes, but it has according to me, it has to change if you want to leverage the complexity of the designs today. Uh, Again, compared to electronics, I think that we are still at a lower level of complexity, and necessarily you will need to, because what you see in electronics is that there would be some people like architects like really thinking a very high level, and working on schematics is actually also helps working with big teams in parallel, whether it is in the layout, whether it is in all kind of aspects in the simulations. If you start with the schematics, so you give the direction where you're going, and then this actually allows teams of dozens, if not hundreds of people on the same design, which I think today is very difficult if you start from the layout. That's maybe very optimistic, but I think that in a few years from now we'll be in that configuration. At least that's what we hope. We need to work on that in that objective.
Okay, so there's another question I just see here, which is a question for Amit. But either you or Amit can answer. But how do you control the thickness of the wafer?
Yeah, I'm gonna hand over to Amit. Thank you. Thanks to all of you. I'm still here in case there is more questions.
Great, thanks, Youssef.
Hey, Lucas.
Hi, Amit. So I noticed there's a question for you as well that cropped up, which is how do you control the thickness of the silicon? So you have lots of measurements on them, but what do you do to control it?
Well, we have two methods. One is, of course, that on certain lots which are priority for our customers, we can actually do hand picking. So that's one way of making sure the wafers supplied to them meet the benchmark that we have set to on control of the top SOI. But we also have a process called through which we use, let's say, post-processing and redeposit crystallized silicon. imec has a patent on this using let's say, CMOS tools to planarize the top surface of silicon from something that was as bad as plus minus 8, 9 nanometers to within plus minus 2 nanometers. So there's two approaches.
Is that a polish deposit, or what's the?
No, it's not. It's not polish. It's more. It's really using plasma to redeposit silicon from areas. First, there is a mapping done of the whole surface of silicon, and then redeposit and crystallization.
And it's a selective deposition based on
yes, based on the previously acquired wafer map. Yeah.
Wow. Okay. Interesting. I didn't realize that. I've been quite curious how you guys do that. Okay. So is that described actually somewhere in a patent that I can read about? Or?
Yeah. It is. It is. I can send a link of that to you.
Oh, that'd be great. Yeah. No, I can add it to the discussion group here. That's quite interesting. I thought maybe you do some sort of selective polishing, but selective growth. That sounds really interesting. Okay. Great. So I think that's all the questions that I see here, unless somebody online who's with us has any more questions. I think we're drawing to an end.
All right.
So yeah,
okay.
Amit, can you please share the link to, or who should we send the NDA to?
I'll provide Lucas a link to both the the link to download the NDA as well as to supply your signed and scanned copies.
Okay, please.
So
that'll be great.
No problem.
And I'll post those. Yeah.
Okay.
Thank you, Lucas.
Great. All right. Well, thank you very much, Amit, and thank you very much, Youssef. If you can pass on our thanks.
Sure. Excellent. Thanks a lot. It was a pleasure to join all of you. And as I mentioned before, if you have got any questions, either through Lucas or feel free to send questions to also our support email address, which I will provide to Lucas. So you can always just send us emails, and we'll be happy to support you on our PDK or otherwise any questions that you may have about imec technology.
Sure. Thank you.
Thank you.
Fantastic. Thank you very much.
Have a nice weekend, guys. Bye.
Yep. Thank you. Bye.